And then we can use bisection method or secant method, okay, or Newton-Raphson method for finding the root of this. So all those converge to this x star 1.4276. For this, f prime x will be 0. And now, once I found this particular root, I will check the second derivative, and second derivative comes out to be minus 2.18. So it means it is a point of local maxima. And in that way, we maximize this point. But there is one more thing. When we are talking about closed interval, we need to check the boundary also. Okay. So if I check F0, F0 comes out to be 0, F4 comes out to be minus 3.11. So it means the value of the function f of x, okay, f of x which is like 1.77, which is maximum for both of these, okay. So it means x star 1.4276 is a point of local maxima or even a point of global maxima, because endpoints also having value lesser than the value at x star equals to 1.4276. Okay. So in that way, that is the classical way we maximize or minimize a continuous function for a given interval. How to do it in Matlab? So one of the ways, just you find a root. Okay. So once you find a root, you give this command. You can try if you are having Matlab with you right now in front of you, or otherwise I will share the slide and you can practice later. Because if you will do now, it may take a lot of time and we will not be able to cover what I want to convey. So fp at the rate x, so it is giving that my variable is x, and then you can pass out the function semicolon, and then once you define this your fp, so fp is a function of x and the definition of function is given by this particular thing. Then once then you call this command f0 on fp and the given interval, and it will give you access, which is the where this function is 0. Okay. So that is one of the way for finding the root. So given a function, how you can optimize it? You calculate the derivative and then find the root. Or you can use the direct 1D minimization of minus f. So for that, I am having this command in modern optimization toolbox. You define your function f, okay. So at the rate x, again the same. This is the definition of the function, because my function is 2 sin x minus x square by 10. And then you call this functionality f mean b and d, and you have to pass your variable. And since I have to maximize, I am using a command of minimization. So I have to give minus of f and then the interval which I am having. It will give you again the same answer. Okay. And then you can use problem based also. Like you pass x equals to optim_var. Okay. To optimize the variable x, lower bound is 0, upper bound is 4 for the, that is the interval in which this guy x live. And then you can define your objective function, and then you can call the solve command. So optim problem objective equals to this function. Okay. So that's all. It will choose the relevant solver and it will give you. Okay. So these are the three ways which I told you, that three workflow for this 1D problem. So that we used to do in our class 11, class 12, maxima and minima of 1D function. But the same kind of syntax can be used for a vector valued function also. But let us go to next one, and next one is how to solve linear programming problem. So all of us who ever gone through the basic course of operation research have come across linear programming problem. And then for solving the linear programming problem, we used to have like graphical method, and that's quite good. If I'm having only two variables, then I used to have simplex method, dual simplex method, active contour methods, and many more. So for a linear programming problem, my objective function will be linear. That is kind of a fine in X. Okay, and constant will also be linear. And constant can be of both type, like inequality constant as well as equality constant. And then we will be having some bounds on decision variables. So for example, this is an example of a LPP where I am having the objective function. I need to maximize Z, which is nothing just 4x1 plus 2x2 plus x3. The first constant is 2x1 plus x2 less than equals to 1. The second constant again x1 plus 2x3 less than equals to 2. And the third constant is x1 plus x2 plus x3 equals to 1. And here x1, x2, x3 all are between 0 to 1. Or x1 and x2 and x3 is between 0 to 2. So I'm having three decision variable, two inequality constant, one equality constant, and a box bound on the decision variable. So now how to solve this LPP in Matlab? So one of the way of solving this problem is by using the lin probe. Okay. So how for using the lin probe, I need to pass certain variables and matrices to this functionality lin probe, and what are those? So if you compare your problem with this particular thing, the problem is maximizing Z. So maximizing Z is nothing just equivalent to minimizing minus Z. And when you are, because lin probe will work for minimization, so that's why I convert it into min. And when then the coefficient of in the objective function will become -4, -2, and -1. So this is my f. So f is nothing just -4, -2, and -1. Then I need to pass this equality constant matrix. So how many inequality constants I am having? Two constants. So if I talk about the first constant, it is 2, 1, 0, because 0 is the coefficient of x3. And the second constant is 1, 0, and 2. That is my matrix A. Then I will pass B. B means right hand side of the inequality constant. So it will be again a vector 1, 2. So B will be 1, 2. Okay. A is a 2 by 3 matrix. First row is 2, 1, 0. Second is 1, 0, 2. Similar thing we will do for equality constants. So if you see the equality constant, yeah. So equality constant is 1, 1, 1. So this vector I will pass. It will be a 1 by 3 matrix. And the right hand side will be 1. So AEQ and BEQ will be these two things. And then I will pass this lower and upper bound. So the same thing we are doing. So we are passing these matrices and vectors. And then I am calling this lin probe command. I will get the function value, the optimum value of the function, and the same time, the value of decision variables. If I call this command, the output will be like this. Optimal solution found, x is 0.5, 0.5. So the function is having maxima when x1 is 0.5, x2 is 0, and x3 is 0.5. And the functional maximum value of the function, here f value will come out to be -2.5. But since This works for minimization, and minus of that minimum value will become the maximum. So maximum of z will become 2.5 at this particular thing. Okay, so this is the easiest way of solving a linear programming problem. Whatever be the number of variables, whatever be the number of inequality constant, whatever be the number of equality constant. Okay, it will work very well. It may happen that certain problem doesn't have equality constant, certain problem doesn't have lower bound or upper bound, or so and so on. So if something is missing in your problem, what you can do at that particular place, you can pass this the empty matrix. Okay. So for example, if no lower bound, so instead of LB, you will pass this empty one. If you don't have any equality constraint, then you can pass these particular empty matrix at those particular places. Okay. So that is the easiest way of solving linear programming problem. We can have other two workflow also. Okay. Like Optimware. That is the another way of solving the same problem. If you don't want to write those bigger matrix, it is like your problems only. So I want to, that is the second workflow. I want to, I will call optim variable. Decision variables are under vector X. Number of vectors, lower bound, upper bound. And then in problem, I will pass the sense of the optimization, whether maximize or minimize. I will pass the objective. I will pass the constraint. Okay. And I will pass the lower bound, upper bound is already given. So inequality and equality constraint. And just I will call the solve functionality, and I will give the argument of probe, because now this probe is having all the information is there. What is objective function, what kind of constraints, and what is the exact constraint, and it will again give you the solution. If you want to minimize it, instead of maximize, you can use minimize. If you are having more number of uh, constraints, you can write it here. Okay. So that is like, just like your problem, you are writing your problem, the same thing. So that is the second way of solving LPP. If you don't want to use lin probe. And this is an example of this. Like if I am having like 6 constant, my objective function is minus x minus y by 3. And I want, and this is my objective. This is the problem. So the optimum is at the vertex C1. Like here you can see when x is 2 by 3 and y is 4 by 3. Okay. And all these are satisfying on these. So this is the feasible region. Okay. And you know, it is a feasible region of a LPP is always a convex region, convex set. And it is, you can see from here, it is a convex set. And the optima will lie on a vertex. So beyond linear programming problem, we are having many more things like quadratic programming problem, very popular in inverse problems and having lot of applications. Then we are having unconstrained nonlinear programming problem. We are having constrained nonlinear programming problem. All these problems we can solve using these optimization toolbox solvers of Matlab, and as I told you earlier also, for like you are having lin probe for linear programming problem. In the similar fashion for quadratic programming problem, you are having this quad probe. And then you are having for unconstrained, you are having fmin UNC, and for constant fmin form. Okay. Okay. So this is the like we are having necessary and sufficient conditions in case of one variable function. If you want to minimize or maximize a multiple variable function, okay? So your problem is a vectorial optimized. You are having vectorial functions. So for minimizing f, which is a function of variables like x1, x2 up to xn, and it should be of twice continuously differentiable. So if it is twice continuously differentiable, the necessary condition will be that x star will be a point of minima or maxima only when the gradient of f at that particular point must be a zero vector. And the second order Hessian of f will be a positive semi-definite matrix. And sufficient condition is like if this Hessian is a at that particular point x star where gradient is zero is positive definite, then x star is strict local minimizer. And to check it whether it is a global minimizer, if you are having closed region, then you can see check value at boundaries also. And what is the meaning of this positive definite? Positive definite means we will say a square symmetric matrix is positive definite if for any non-zero vector x coming from n-dimensional vector x transpose Ax, which comes out to be a scalar, this particular thing is strictly positive. For all x, you choose any non-zero x, the vector x. Or the easiest way of checking it, because from there, using the definition of eigenvalues and eigenvector, we can prove that if a matrix is positive definite, then it's if and only if its all eigenvalues are strictly positive. If all the eigenvalues are strictly negative, we will see it negative definite. If it is like 0 is also involved in both the case, we say positive semi-definite or negative semi-definite. And if eigenvalues are positive, negative mixture of both, then we said it semi-definite. Sorry, indefinite. Okay. So these are the optimality conditions for a unconstrained minimization problem in n dimension. And let us take an example and then we will solve this example using Matlab. So suppose I want to minimize this function f of x1, x2, and the function is defined as e raised to power x1 plus x2 minus 1 plus e raised to power x1 minus x2 minus 1 plus e raised to power minus x1 minus 1. Okay. Suppose I want to solve this particular problem. Okay. I want to minimize this function, which is sum of three exponential function. And these three exponential functions are functions of more than one variable. Means of two variables. Okay. So to minimize this particular problem, I will write the problem in this form. Minimize. Okay, I will come to this later because here we have given the classical solution. So what I will do, I will find the partial derivative of f with respect to x1. I will find out the partial derivative of f with respect to x2. And by solving those two equations, by putting them equals to 0, I will get the point x star, critical points. And then I will create the Hessian matrix, and then I will check the nature of Hessian matrix at those particular critical points. Okay. And here we are seeing that del square f is positive, so it is a convex function, means problem is convex. Because Hessian is positive definite here. Okay. Anyway. So if you are having quadratic programming problem, because we will come to this nonlinear problem later. Let us first talk about quadratic programming problem. So the standard form of a quadratic programming problem will be like this. Minimize half x transpose hx plus ftx. So this particular thing will encode the quadratic part and it will encode the linear part of the function. So here objective function will be quadratic, whereas constant will be linear, like in linear programming problem. Okay. And here this H matrix will be a symmetric matrix. Means all of you know how to write a quadratic form. So for example, uh, if I am having like a problem like minimize f of x1, x2, which is equals to, let us say, x1 square plus 2x2 square plus x1, x2 plus 3x1 plus 2x2. So this I can write as uh, uh, x1, x2, and I will write like half, and then it will be 2, and this will become 4, this will become 2, 2, or 1, yeah. 1 from here, 1 from here, and then x1, x2, plus ftx. So I will be having x1, x2, or ftx if you want to write like 3, 2, and then x1, x2. So this is your matrix sets. Okay, which I am writing like xthx plus ftx. I am writing it. And this is your vector A. So if you solve it, multiply the matrix, you will get the same objective function. So now I am having x, I am having a, and then easily I can use the quad program functionality of, yeah. So x, you know how to write, f, how to write, and these will be like LP only, like you do in linear programming problem. And then you will use this command, quad pro, you will pass h, f, and these will be similar to LP, okay? Because it is coming from the set of constraints and bounds, okay? So in that way, you can solve a quadratic programming problem very easily using Matlab. And this quadratic programming problem is having lot of applications like least square fitting, portfolio risk, because we can model our portfolio optimization problem as a quadratic programming problem, model predictive control, which are again models in terms of a quadratic programming problem. Support vector machine in machine learning is nothing, just solving a quadratic programming problem. And then TV denoising, total variation or Tikhonov regularization, denoising, that I will show you one application of this. After quad pro, so we have solved LP, we have solved quadratic programming problem. Let us move to NLP. So the example which I was telling you earlier, this particular example. Suppose I want to solve, I want to find out the minima of this. So how I will do? I will define my function f, the variable is x, and which is a vector variable having x1 and x2, two component. This is the objective function I will define. The same function which I want to minimize. Now, optim option I will give the unconstrained function minima. What kind of algorithm you want to use? Whether quasi-Newton or BFGS, there are a certain number of algorithms. Okay, and so on. So if you see, this is the function, this is the display, and once you pass this, the value of the decision variables at at minima, and the functional value, you will pass your function which you have defined in the first line. Here you will pass it here. You will pass the in which interval, in which domain you want to solve your problem. So let us say both are from -1 to 1. And then this particular thing, which method you want to use, and so on. Once you run this command, you will get the value where the function is having the minimum value, like at x1 equals to -0.3466 and x2 equals to 0. And what is the minimum value of the function at this point? So very easily you can find the you can solve this unconstrained optimization problem. So this is the one example for that quadratic one where I was telling that how you can model your quadratic programming problem using this portfolio optimization problem using as a quadratic programming problem. And then you can solve it using the command quadprog. So for example, you want to invest a budget of 1,000 unit across 3 assets with expected returns like 2.6% from the first asset, 0.8 from second, 7.4% from third, and the covariance matrix sets given below. Okay, this one. Objective is minimum variance portfolio earning at least 50 units of expected return. So you can write your problem like this, minimize the risk, this one, and then total budget is 1,000. This is your constraint. So these are coming constraint. And once you pass it in the quad prog, you will get your answer. Like here, I have passed, and answer comes out to be 500 in first asset, 500 budget in the third asset, and 0 budget for the middle asset, the second one. Okay. So if you are having all these data, you can solve that problem using quad prog. Okay. Then there is a general purpose solver because we have started with LP. The simple function, 1D function, function of one variable, then LPP, then quad prog, then unconstrained nonlinear NLP. If you are having constant NLP means you are having an objective function f of x which you want to minimize, and then you are having set of equality and inequality constraints, and okay, and then you are having a linear constraint, and finally lower and upper bound on x. Okay, so for this nothing, again you have to write all these metrics, like you will write you will use the fmin con command in the same way you use fmin unc. You will pass your function which you have defined, x0 initial solution, a b aeq b qlb, and so on. And once you will do it, you will get the answer. Okay. So like lin prog for linear programming, quad prog for quadratic programming, uh, fmin unc for unconstrained minimization, NLP minimization, fmin con for constraint minimization. And this is an example. Suppose you want to solve this problem, you want to minimize this. Let me write in a more better way. 4x1 square plus 2x2 square plus 4x1 x2 plus 2x2 plus 1. Suppose you want to minimize this function. Okay. And subject to the constraints are given like this one. It is a nonlinear constraint. X1, x2 minus x1 minus x2 less than equals to minus 1.5. And then x1, x2 greater than equals to minus 10. You define your function. It is similar, which you have done in FMIN UNC. Then you will define all your things like constraint and so on. Second constraint, FMIN call algorithm which you want to use. There are choice of algorithm. And once you call it, you will get the answer. Like this is the what I will say, the x value of x1 and x2 on at which this function is having the minimum value, and the minimum value is 0.0236. You can verify all the constraint whether it is satisfying or no, and so on. Okay. So these are about the optimization, because most of the problems comes in any of these 4 to 5 categories which we have discussed. Now let us move to second part of my talk. This is another problem. If you are having, let us say, system of equations like find x1, x2, and these two nonlinear equations you are having, you have to find out x1, x2, for which which is the solution of these two equations, nonlinear equations. And in mathematical modeling, we quite frequently solve such kind of nonlinear systems. And using the same approach, you can find out, okay? You are using the same approach. Define your function and so on. And then you can use solver. So, now come to the other part. Let us move a bit from optimization to linear algebra. And in linear algebra, I will talk very simple thing, but which is having like applications like anything in AI, machine learning, and so on. Okay. But these are the base, okay, foundation of AI. If you are having a linear system, X equals to B. Okay. And where A is a M by N matrix and M is not equals to N. It means I am having M number of equations and M number of columns. Okay, M number of equations and N number of variables, not column. Okay. So now there may be two cases. M is greater than N. M is greater than N means you are having more number of equations, less number of unknown. In this case, what will happen? It may happen there is no exact solution, because if I say x1 plus x2 equals to 1, second equation I am writing x1 minus x2 equals to 0, and third equation I am writing x1 plus 2x2 equals to 0. So now these are having three equations, two unknown, and this particular thing may not have, it doesn't have an exact solution. Okay. B is not in the range space of A. I want to say like this in terms of linear algebra. So if this is not how to solve such a system? If there is no exact solution, we go for approximate solution. Okay. An approximate solution, how we find? We find minimizing this particular thing. Minimize Ax minus B and L2 norm of this. So basically what I want to say, I am having a system. Let us say A is the coefficient matrix, then X equals to the right hand side vector B. Okay, I want to solve such a system. A is m by n, and when m is greater than n, it is a overdetermined system. And in this case, we go for OLS, ordinary least square solution. So how we solve it? X equals to B. I multiplied both sides by A transpose. So now this matrix A transpose A become a n by n matrix, square matrix. So you converted your rectangular system into a rectangular overdetermined system into a square system. Okay. And then the solution of this can be obtained by multiplying both sides by the inverse of A transpose A. So A transpose A inverse AT into T. Okay, and what this guy is called? It is called pseudo inverse of A. Pseudo inverse of A. And what is this? Whatever solution you will get from here using this, it is nothing, just it is equivalent to finding such a solution X which minimize this matrix norm. This matrix norm. So for example, I told you a problem, x1 plus x2 equals to 1, x1 minus x2 equals to, let us say, 0.1, and x1 plus 2x2, let us say, I am saying 3. This doesn't have, or let us say it is half. This particular system is not having a solution. Exact solution, exact means the value of x1, x2 will satisfy both all these three equations simultaneously. So what I do, I define this objective function E, which is nothing just x1 plus x2 minus 1 square plus set from the second equation, I will get this one. From the third equation, I get this one. Okay. And I find out such x1 and x2 which minimize this E. And this can be solved by this method also. So this is the calculus approach. How you will do it? You will find out del E over del x1 equals to 0. Del E over del x2 equals to 0. Okay. And from here you will get two linear systems, 2 by 2 linear systems, and which is equivalent to this one only, this system only, this particular system. Okay. And then you can find out the solution. Okay. So in that way we can find the solution of ordinary least square. Okay. In the second case, I can have m less than equals to n. Okay. M less than equals to n means you are having few equation and more unknown. Very few observations, but from those observations, you have to calculate, you have to find out many value of many variables. You have to make more number of predictions. So such a system is called underdetermined system. And you know, when we are having few equation more unknown, we will be having infinitely many solutions. And in case of infinitely many solutions, we pick a solution which minimizes the norm. Okay, which minimize the norm. So for example, I am having a equation x1 plus x2 equals to 1. So this particular equation can have a solution x1 is 1, x2 is 0, x1 is half, x2 is half, x1 is 0.4, x2 is 0.6, so infinitely many solutions. So out of all these solutions, I will take a solutions which minimize the L2 norm of the solution. So for example, what is the length of this? The length of this is 1. Length of this will become 1 by 4 plus 1 by 4, 1 by 2. And then you will take the root, so 1 by root 2 and so on. So whichever will be having the minimum length. Okay. That solution I will find out. That will be useful to me. And if m equals to n, then and a is invertible, then solution will become x equals to a inverse b. So how to do it, how to solve all these problems like least square minimization, this least ordinary least square, all these in Matlab. So this is what I was explaining you. This is the theory behind it. Sorry, I am not explaining it. So the easiest way of solving such a system is, one of the ways using this backslash operator. Okay. You write your matrix A, you write your right hand side vector B, and x equals to a backslash B. You run this command. That's all. It will give you the solution. Okay. The second solution is, since you have written your matrix A, you find a pseudo inverse of A by using P inverse means pseudo inverse of A into B. So it is nothing but that solution ATA inverse AT. This is the pseudo inverse of A. This guy into B. So this is x equals. Okay. The third one is LSQ mean norm LB. It will again give you the minimum norm least square solution. But if you use this particular technique, it will make you the singular value decomposition for finding the pseudo inverse. Here we will find the pseudo inverse means this solution using the orthogonal decomposition, and it is faster than P inverse. If you are having like thousands of variables and let us say 400 to 500 equations, then this particular approach might be slow. In that case, it is a better choice. And the final one is LSQRAB. Iterative least square using AX product. And it is a numeric approach. Okay. If you are having very large sparse matrix A, sparse means very few entries of A is non-zero. Okay. So such a system is called sparse system. If you are having a sparse system, this is the best choice. Okay. So that is a table which will give you, because we are having all these four options to solve X equals to B, whether overdetermined or underdetermined, but when to use which method. Okay. Here I have summarized that in which case you should go for what kind of method. Okay. Yeah. So this is one of the example of solving 2x1 plus 3x2 equals to 8. And I am using two methods. So the problem is to solving this. So it is a underdetermined system. Underdetermined system. So what is my A? A is a matrix 2, 3. Coefficient matrix. Right hand side, only one equation, so B equals to 8. One of the way using backslash operator. Okay. And it will give you the solution, this one. It will give you the solution itself. The second one is LSQ mean norm. LSQ mean norm if you are this one using the orthogonal decomposition, or the same answer you will get with P inverse A. Okay. So if you use any one of these two instead of this, then the answer comes out to be this one. Because it is a underdetermined system, it will be having infinitely many solutions. So what is the difference between these two solutions? It is a minimum norm solution. The norm of this vector is minimum among all the vectors those satisfy this equation. However, it is a sparse solution. Okay. So sparse solution means many of the variable solution vector will be having many zeros. Okay. Many of the variable will be having the zero value. So this particular technique is good when you want sparse solution. And when you want to have a sparse solution means when you want to find out some of the important variables. Only you want to keep alive them and want to kill other. Okay. So they will become zero. Killing means they will become zero and so on. And if you want mean norm solution, you want a smooth solution, then you will use LSQ mean norm. Okay. So why I am saying this? Because minimum norm solution means you are minimizing norm of x subject to the given ax equals to b. So what is this guy? This guy is nothing just minimizing x1 square plus x2 square. Minimizing x1 square plus x2 square. And it is nothing just, if you see the geometrically, this is the radius of a circle which touch this line. Because this 2x1 plus 3x2 equals to 8. It is a line. Any point on this line will satisfy this equation. Any point in this line will satisfy the given equation. Now, you want to, among all those points, you want a point which minimizes this distance. So when it will minimize it? When this particular line will be a perpendicular to this one. Means at a point on which this line is a tangent to this circle. Okay. Because if you take any other solution on this line, then the minimum norm x2 will become more than this one. This will be the minimum one. Okay. So that's what I want to convey. Okay. Okay. Yeah. So this so far we have talked about L2 norm that minimize x2 subject to ax less than equals to b. No, not less than equals to, so equals to b. Because we are solving the linear system. Okay. And in case of underdetermined system where you are having infinitely many solutions, among those infinite many solutions, you want a solution which minimizes the length of solution vector. Okay. Having the minimum length. There is another thing which is called x norm. Okay, or zero norm of x. It is called L0 norm. In reality, it is not a norm, but what the meaning of this particular thing is the number of non-zero entries of x. So, for example, if x is a vector 1, 0, 2, 0, 2, 0, 0, 1, then this particular value will be number of non-zero. So 1, 2, 3, 4. It will become 4. So now I am posing my problem in a different setting. I want to minimize subject to, sorry, equals to ax equals to b. So ax equals to b when a is underdetermined, you are having few equations, more unknown, it will be always having infinitely many solutions. Among those infinitely many solutions, I want to find a solution which is having the minimum zero norm, minimum number of non-zero entries. And believe me, this particular problem is having lot of applications in AI, like dictionary learning. It is having in like compressive sensing and many more applications. So how to solve this problem? Means I want to explain the measurement with the fewest active components. If I use LSQ mean node from the Matlab as I shown you earlier, it picked the smallest energy solution. What I need? I want the smallest support, means which is having the minimum number of non-zero entries. How to solve this problem? Basically, it is a NP hard problem. It is a NP hard problem. So this, let us name it L0 problem. This L0 problem is NP hard problem. Means we don't know any whether the problem can be solved in polynomial with polynomial running time complexity. And since it is NPR, so what is the escape route? So I will replace this L0 by L1. Okay. And then it can be solved using a greedy approach like orthogonal matching pursuit and so on. So what is this L1 minimization? In earlier case, I was solving the problem like minimize x1 square plus x2 square, and let us say square root of this subject to whatever, let us say x1 plus 2x2 equals to 5. This is your L2 minimization which we were discussing. Like I have shown you this particular diagram. This one. What is L1 minimization problem? In L1 minimization problem, instead of minimizing L2 norm, I will minimize the L1 norm. Like minimize x1 plus x2 subject to x1 plus 2x2 equals to 5. And this minimizing the sparse norm, L0 minimization, I will approximate with this problem. It is a convex optimization problem, and we can have some greedy solution for solving it. And under certain conditions, the solution of this particular L1 minimization problem will be similar to your L2 minimization problem. Sorry, L0 minimization problem. So why this L1 minimization give you the sparse solution? Why it is giving you the sparse solution like you were getting here, like in this case? In this case, it is a sparse solution because among two variables, one of the variable becomes 0. Whereas it is not a sparse solution. Both the variables are non-zero. So why it give you the sparse solution? It can be seen by a geometry very easily. Like this is the L2 which I explained you. It will minimize this. So it will come like all solution. Let us say alpha x1 plus beta x2 equals to, let us say, delta. It will be a line, and any point on the line will satisfy this equation. So all are solution, infinitely many solution. In L2 minimization, I will choose this point. Okay. The point where this circle will be having, I will start like this, like this, like this. And then when it will touch the line at a point, I will get this is my solution, L2 solution. However, in L1 minimization, you see the shape of the objective function. The shape is not a circle now. It is having this shape, quadrilateral kind of thing. Okay. And when I will start like this, like this, like this, what will happen? because every point on this line is a solution. So where it will meet the line? It will meet at x at where on the y-axis or x-axis. So from this 2D visualization, we can see y x1 whole is giving you the sparse solution. Okay, and minimizing this x1, L1 norm minimization of x subject to x equals to y is a convex problem. We can solve. Okay, and we are having solver for it in Matlab, and in that way we can if the L1 this the coefficient matrix A and the sparsity condition satisfy these two results, means RIP property, then it will give you the solution of L0 problem also with certain admissible sparsity. So I am not going into this theory. Let me show you how we can solve the L1 minimization problem using Matlab. So what is L1 minimization problem? Basically, it is nothing, just your LPP only, okay, a kind of linear program only. And so if this is the only thing, what will happen? Your number of variables will become 2 times, because I will split this x decision vector with edge u minus v, where both are greater than equals to 0. Okay. And then everywhere I will replace x by u minus v in all constant in objective function, and using that it comes out to be a linear programming problem with equality constraint only. And using lin probe, I can solve the problem. Another way of solving it is using some greedy approach like orthogonal matching pursuit. I am not going into detail, but it can be coded very easily in Matlab. Okay. Like this is the example. Okay. This is the example. So this simple function OMP, I will pass a coefficient matrix y, right hand side vector, and k, the sparsity which I need. And then I will run a for loop from 1 to k. Each time this orthogonal matching pursuit, what it will do? It will find out a column of a to which it is having the maximum covariance, and will take that covariance one of the solution, and in that way it will go. And then we will remove it, we will go again. So we will look for the greedy solution. So using 3, 4, 5 lines, we can write this orthogonal matching pursuit solver in Matlab. So let me summarize it. If you are having this L1 minimization problem, you can use either lin probe, or you can write the solve functionality, which I am having here, OMP, by writing the OMP. There is a lasso regression where again we use this x1. So there is a lasso toolbox. Here you pass out a equals to 0, and you can solve using lasso also. You can use greedy approach like OMP, and many more many more algos. So there are 5 ways of solving this L1 minimization problem. What are the applications of all those? So one of the application is total variation. Okay. So suppose you get a signal which is noisy, or you get a image which is noisy. You want to clean the image. You want to denoise it. How you will do it? So suppose you got a signal Y. Ideally, you should get a signal X but instead of x, you are getting a signal y, which is x plus some certain noise. X is okay, and this noise is uncorrelated with x. Okay, so how to reduce or remove this noise? Means given y, how to find out a good approximation of x. So this problem I can modify as a L1 minimization problem that minimize the difference between x and y, L2 difference between x and y, plus minimize the total variation of x. Because x is a noisy signal. X is a noisy signal means a noisy signal will be having lot of variation. So you just minimize the variation of x also. Okay. So here you take L1 norm, here you take L2 norm. So your problem become a L1 minimization problem. And now solving this, you can get the clean signal from a noisy signal. And example is here, code is here. You can try this code. So actually here if you see the left figure, this blue solid line is my original signal. I should have this signal ideally. But let us, due to some sensor error, due to some other artifact in the system, instead of getting this clean signal, I am getting this noisy signal, noisy version of it. So this, the light blue one, it's noisy signal, noisy version of it. So now TV denoising is nothing given this noisy signal. Find out a good approximation of this clean signal. I don't have this clean signal. So you can model this problem as a L1 minimization problem. As discussed in the previous slide, you solve it using LinProg or any other. I told you that 5 different method of solving it, and you apply it, you solve it, and then this is the result when you are solving it using Optim problem solver. Okay, solve functionality. So red one I am getting now. Okay. So you can see the red one is very close to the blue one. A very good approximation of blue one. This is not so not, and you can apply it on any dimension signal. It is a 1D signal. In image denoising, which is a very fundamental problem. Okay. The famous model of Rudin-Osser, Fatemi, it's nothing, just it is this one only. Okay. So all these are inverse problems, and we can solve using these very basic approaches and by coding it in Matlab. So suppose I am getting this image, this is the ground truth, but suppose due to some sensor error or any other artifact, instead of getting this image, I am getting this one, noisy version of this. I can again apply, I can model it in the same way as a L1 minimization problem or L2 minimization problem, and I can get the clean version, smooth version of it, where noise is not that much. Okay. So that is another application of these. Low rank sparsity. In many applications, even in AI also, when I am having matrix of model parameters, I want to store it with low rank approximation. This again the L1 setting give me the low rank approximation also of a matrix. Okay. And it also can be used for background and foreground separation. So for example, given this image, you apply the L1 minimization, I will get the separate version of it. Okay. L0 or L1. L0 means ultimately you will apply L1 to only. Suppose you are having a matrix and many of the entries in the matrix are missing. So for example, on the row, you are having certain movies. and on the columns you are having users. And here let us say every user is not seen each and every movie. So what will happen? Many of the entries of the matrix of this recommendation matrix will be missing. And this is just an example I am saying. Many real life problem we can model this uh, missing entry recovery problems. Okay. The famous Netflix problem is also this particular problem. How you can solve this problem? So okay, because many movies has not seen by many of the users and hence they didn't give the recommendation. Okay, so how to fulfill, how to complete this matrix using their recommendations? That again we can model it into L0 minimization program. Okay, and using that L0 minimization by the same setting, by the same Matlab code, you can solve this particular problem also. Why I am saying I can model it? Because the concept is very simple. If two movies are, let us say, similar, same category, let us say both are comedy, same kind of actors, same kind of director, story is similar, they will be having very similar recommendations by different users. When they will be having similar recommendations, the two rows will be very close to each other. And when two rows are very close to each other, we can say those two rows are dependent to each other. Okay. Okay. So it means if they are dependent to each other, if there are missing entries, we can fill. And how we can fill it? If many of the rows are dependent to each other in a matrix, matrix will be having low rank, very few rank. So by minimizing this rank, we can solve this matrix completion problem. Or this is famous, and matrix completion can be used in recommender systems, in many systems. So what I want to say, we can solve many real life applications using these simple methods. There are many more applications I don't want to go, like background on the movie. So a video is having a sequence of frames, a sequence of image. And in this sequence of image, what will happen? Only foreground will move. Like the background behind me is not moving, only I am moving. Okay. So when I am, so how to extend? So suppose now I am live. Okay. So each and every image of this sequence is sending to various users. Okay. Going to various users. So since my background is constant, why to send it again and again? Let us send it to once and then only send the foreground, this particular area. So for doing this, what will happen? In each frame, I need to extract foreground from the background. I need to make both of them separate. This again we can model in L0 minimization problem. Okay. Just a convex program, separate the two very easily. And this is applicable to many video surveillance applications. To make the processing faster, to make the transmission faster, and for many other operations, many other applications. So, what we have learned? We have learned the modern toolbox of that is optimization toolbox. Okay. For solver, one pattern like link probe, quad probe, fmin, unc, fmin con. The syntax are almost same. And we can use these to solving different problems. In the next stage, we have learned how to solve rectangular systems, what is least square, what is minimum norm solution, how we can apply MATLAB to them, and then from L2 to L1, and then we move to L0, which is NPR cannot be solved with JULY. For that, we have approximated to L1, and then we have seen how we can solve in L1, just writing the 15 lines of Matlab. And then this minimization, L0 minimization problem, L1 minimization problem is having lot of applications. Some of the applications I have just introduced you, like noise denoising, TV denoising, total variation denoising, RPCA, matrix completion, background extraction, and so on. So thank you, and I welcome your questions. These are some of the
Thank you, sir, for this nice and informative talk. Now I request to the participants for the question and answer section. If they have anything, feel free to ask their questions, their queries. Sir is there. At least I would like to ask or to expect from all the participants at least 2 or 3 questions should come. Please. I also request to the participants kindly turn on your camera for the group photo, and also I expect for the questions or any doubt if they are having from their level, feel free to ask. At least 1 or 2 questions can be taken.
I think it's fine. If it's fine, no issue. If there is no question, means either they didn't get anything or they got everything. Okay.
Teachers, research scholars, all the participants, please, if you are having any doubt or anything, if everything is okay, then also you should say, you also should interact to our resource person. So if no questions, then I would go with the keynotes or the keywords the sir has covered in his lecture. The session on computer, sir, is there any others? Please, if you have questions, then it's okay. If not, then please mute your mic. So a short summary of this session. Sir has covered in his session computational optimization and sparse norm minimization with Matlab. It is providing an insightful introduction to modern optimization techniques and their applications in science, engineering, and data analysis. Our resource person also has explained very nicely the fundamentals of optimization, including objective functions, constraints, and iterative solutions method, emphasizing their role in solving real-world computational problems. The concept of sparse norm minimization was discussed as an effective approach for obtaining efficient solutions in applications such as image processing, machine learning, signal recovering, and comprehension. Sir also has talked about how Matlab serves as a powerful platform for implementing optimization algorithm, visualizing results, and solving complex numerical problems with accuracy and efficiency. At the end, sir also had discussed about the practical examples and MATLAB-based demonstrations. Participants gained a clear understanding of optimization strategies and sparse modeling techniques. I would say the overall session was conducted by Sir was highly informative, interactive, and beneficial, enhancing participants' knowledge of computational optimization and its practical application in research and advanced engineering. Many more things has covered in his lecture. Now I would request to Dr. Richa Agrawal for the vote of thanks of today's session. Richa
Good
Agrawal, ma'am.
afternoon. Good afternoon to all of you. On the behalf of GCET, I sincerely thanks our respected speaker Sanjeev sir for the insightful and engaging session. Your valuable insights and expertise have greatly benefited us. I also extend my heartful thanks to management, faculty members, and all participants for their support and active presence. Thank you, sir.
Thank you, ma'am. Now, again, I would request to Dr. Rajiv Kishore, sir, to summarize the lecture. Thank you, sir.
Thank you, sir. Good afternoon to all of you.